All right, so we've talked about three factors so far: the frequency of action potentials, right? The length of the sarcomere, and then the diameter of the muscle. What we're going to move on to talk about here is the idea of recruitment. How can we call on more muscle fibers to generate more force? So this is basically stimulating additional fibers to contract. If we look at the structure of a muscle, it has multiple fibers inside. And usually when we have contraction of the muscle, not all of those fibers are contracting. So calling on additional motor units or additional muscle fibers will generate more tension or more force. Now, this can happen at the level of a single fiber, or it can happen at the level of multiple fibers, which is a motor unit, or it can even happen at the level of the entire muscle, right? Just recruiting more muscle. All right, so let's illustrate what that looks like here. So here's our spinal cord, here's the motor neuron, here are the fibers that this motor neuron is innervating, which is constituting a single motor unit. So we have motor unit X and motor unit Y. Now, if we think about the amount of force that can be generated by motor unit X alone, where it has 5 fibers contracting, this is the amount of force. If we look at the force generated by motor unit Y alone, slightly more, because we have more fibers that it is innervating, so 7 fibers, so slightly more force. But if we use the combined contraction, if we recruit both of these units to contract together, now we're going to add the force, we're going to sum that force together, add the number of fibers, and we're going to have maximum force by recruiting more units. So let's look at the reason why more units equals more force. So if we think about an additional motor unit, it's going to activate all the fibers that is attached to that motor neuron, and that will generate more force because all of the cross bridges happening on those fibers will add to the amount of force generation in total. And if we think about delicate movements, small movements like the movements of the eyes, movements of the fingers, these are going to be associated with smaller motor units. And when we say smaller motor units here, we mean that the size of the neuron will be smaller, the diameter of the fibers will be smaller, the number of fibers will be smaller. So smaller motor units are typically associated to smaller muscles with more delicate or fine movements. In comparison, large motor units are muscles typically associated for strength and power, like your biceps, your triceps, your quads, your hamstrings, your glutes. Those motor units have larger neurons, they have more fibers, the fibers themselves have a larger diameter, and overall, they're going to be generating much more force than we see with muscles for more delicate movements. So let's describe that here a bit. So the motor unit size is going to vary, and everything within that unit will also vary. So small for delicate movements, small motor unit size, small fiber diameter, which will produce weaker movements as well, versus large muscles for strength, which will be associated with um, small muscle fibers, smaller motor units, and then large, I'm saying large muscles for strength associated with larger fiber diameters, also for muscles that are going to give stronger contractions for more powerful movements, right? So everything small and then everything large. So we have this sort of spectrum of contractions and motor unit sizes. Okay. And just to kind of describe here further, so the small motor units have small fibers. The neurons, the motor neurons have small cell bodies. The axons on those motor neurons have a smaller diameter. So really everything about the motor unit is small, right? This is what I mean when I say that it's a small motor unit entirely. Whereas large motor units have large fibers, the neuron, right, the motor neuron is going to have a large cell body as well as a large diameter of the neuron itself. So not only is the fiber that's being innervated having a larger diameter, but the neuron, the motor neuron itself also will have a larger diameter if it's a large motor unit or a powerful muscle. Let's talk about the size principle. So when we have recruitment of additional motor units, you always recruit with the size principle. So the order of recruitment is related to the size of the motor unit, where smaller units are recruited first. And this makes sense, right? This is just more efficient for the body. If you're trying to lift a light object, you're going to start with the smallest units first. As the weight of that object increases, you're going to recruit smaller units first, then you're going to go to larger units last. All right. The reason for this is that it's easier to depolarize a smaller neuron than it is to depolarize a larger neuron to get to threshold or to fire the action potential. So it's going to require greater synaptic input, right? More energy, more synaptic vesicles, more neurotransmitter, more receptors. It just requires more effort to recruit a large motor unit. And so just to be more efficient, we're going to recruit those units last when we absolutely need to power those stronger contractions. All right, so here's the spinal cord again. Here is a small motor unit X, a medium motor unit Y, and then a large motor unit Z. And the tension generated by each is incrementally more. And we would recruit in that order. We would recruit X first. If we need more force, we recruit Y next. If we need more force, we recruit Z ultimately. All right. Now, the last thing that we're going to discuss here is the velocity of shortening. So when the muscles contract isotonically, we want to think about how quickly that contraction occurs. So the latent period or the shortening is going to increase as the load increases. Okay, what does that mean? As I'm lifting a heavier load, the time that it takes for the machinery to get warmed up is going to increase. So as the load increases, the latent period too will increase. All right. As the load increases, the duration of shortening decreases. Again, just to put this into a more practical example, if I'm lifting a very heavy load, the duration that I can carry or sustain that load is going to decrease as the load gets heavier. Right? If you ask me to stand here with a plastic bottle that's empty, I can do that for a few hours, but I would not be able to do that for very long periods as the load gets progressively heavier. So the duration of shortening decreases as the load increases. Lastly, the velocity of shortening decreases as the load increases. So as the load gets heavier, the speed with which you can get to the maximum contraction will decrease. And you can see that on the curve here. So here's the shortening velocity, which is the speed of the contraction. And then here is the load at its greatest. So when the load is zero, the velocity is the fastest, right? I can lift a very light object very quickly. As the load gets to the maximum, which is down here, the velocity becomes very, very slow. The velocity is low. So as load is high, velocity is low. As load is low, velocity is high. All right, so that is kind of how the speed of the contractions change with regard to the load. Okay, and then this is just comparing the slope of those curves. So the slope here is equal to the velocity of shortening. And as we can see, the heaviest load, which is here, right, when the load is extremely heavy, the distance shortened is at its lowest or shortest. The latent period is the longest. Remember, the latent period is the time before the force generation starts. So there's a longer latent period. And the overall length of the contraction is the shortest. So we're not able to sustain this contraction for as long as if the load was zero. So if the load were zero, the latent period is almost zero. The distance shortened is the greatest, and the duration of the contraction is going to be the longest, right? We can sustain that contraction for long.